All right, so now that we just talked about planetary scale, now let's work our way down to talk about the rest of them. We spent a little bit more time on planetary scale in order to talk about the general circulation. Things will go a little bit more quickly from this point forward. So, when we talked about planetary scale, that referred to things that were about on length scales of 5,000 kilometers, or the east-west distance of what the continental United States is. Synoptic scale is what's sort of below that, 1,000 to about 5,000 kilometers. And in that broad scale, that broad large scale wave pattern that we noticed, those waves, the full waves, are on the planetary scale. But the individual ridges and troughs often fall into what we call synoptic scale. Also in this category or this scale range are things like air masses, fronts, and large-scale systems. Those should sound familiar because that's what we're going to be talking about in the second paired lecture of this week. That's coming up next. But there's a few overall details that I want to touch on still here as we talk about synoptic scale. So as a refresher about troughs and ridges, again, troughs in the northern hemisphere are these U-shaped patterns, and ridges are these N-shaped patterns. And these tend to show up both in our mid-level, our 500 hectopascal, middle of the atmosphere plots, and our upper levels, which that we were focusing on when we were talking about the planetary scale. And the waves that we tend to notice in the atmosphere form these ridges and troughs. But when we go down to the surface, instead of having these wave-like patterns, we tend to get things that are more closed off into circular circulations. And we get low pressure systems, again, kind of an analog to the troughs, that look like this, that spin anti or counterclockwise in the northern hemisphere. And then we get high pressure systems that tend to spin clockwise. Now, you notice how I sort of line these up and talk very deliberately. They're connected, and we'll touch on this in just a little bit. So the key idea of how these low-level patterns, these high and low pressure systems, closed circulations near the surface behave, and these upper level ridges and troughs in these upper level waves comes down to convergence and divergence. So convergence is a term that refers to air that comes together, and divergence is air that moves apart. And this can happen in fluids in two main ways, either due to direction, as we sort of see illustrated up here, where it's coming in, flow that's the same speed, coming in from all different directions, coming together for convergence, or moving apart for divergence. Or we can also have it, if we don't change direction, we can have changes in speed that give us convergence, where flow is slowing down, so it sort of has to build up or converge as it's coming together more. Or it moves apart as it speeds up. And so both of these are important to consider when we talk about convergence and divergence, because they both happen in the real atmosphere. So the key idea that links by way of convergence and divergence our lower and upper atmosphere patterns is that the atmosphere obeys something called continuity. This means that the air just can't be arbitrarily or infinitely squeezed in a single location. If you squeeze air, essentially it has to go somewhere. If you have convergence, you'll have to get air leaving that point of convergence. And if you have divergence, you have to have air coming in to fill it. So, since we talked about the upper atmosphere, essentially upper troposphere, that we consider the boundary between the troposphere and the stratosphere, which we call the tropopause, as sort of a hard limit, and the ground, or the ocean surface, isn't a hard limit. We can't have air going into that. We know that that compensating flow for either divergence or convergence has to go away from those two boundaries, which means that If we have convergence at the surface and or divergence aloft, that means we have to have upward flow. So divergence, in order to compensate continuity, you have to have upward flow. And conversely, or vice versa, if we have convergence aloft, that means some air has to go down. Or if we have divergence near the surface, again, the air has to go down. And the nice thing, or convenient, or cool thing about the physics of this is that it can sort of cause the other circulation. That divergence aloft, because you're pulling up air, but that air being pulled up again by the same continuity arguments means that air kind of has to come together to fill the gap that's left here. So these things can influence each other back and forth. So the main driver is our broad scale patterns, which we talked about and focused on, were aloft, upper atmosphere. So where does this convergence and divergence aloft come from? This goes back to why I talked about geostrophic balance. Because geostrophic balance was the perfect or equal balance of pressure gradient force and Coriolis force. We don't get perfect balance when we have curvature or rotation in the flow. Because hopefully this is one little of those high school physics level details that in order to have motion in a circle, you always have to have an acceleration towards what you're rotating around in order to curve your motion. It's the same thing in a fluid. In order to have curved flow, you have to have some component or some net force going towards what you're curving around. So here you have to have a net force towards the trough. Here you have to have a net force towards the ridge. But because of how this is oriented, we're having in this diagram, we have lower heights to the north. Our pressure gradient force is always going to be pointing up. And because our flow is more or less going from west to east, our Coriolis, which always acts to the right in the northern hemisphere, is pointing down. So in order to have a net force towards the center of the curvature in a trough, we have to have pressure gradient force stronger than Coriolis. And the opposite here, in a ridge, we have to have Coriolis stronger than pressure gradient. And the last detail that connects this all together is that Coriolis force is proportional to the wind speed. So that's why you get these little things that are written in on this diagram. Here, where Coriolis force has to be weaker than it normally would be in balance with the pressure gradient force, that means we're actually slower because Coriolis is weaker. Here, the opposite. Coriolis is stronger, which means we have to have higher speeds than what we'd expect from geostrophic balance, where PGF and Coriolis are equal. So that causes in our wave, because of the curvature, to have flow that speeds up or slows down. And again, going back to what we talked about before, speeding up and slowing down are divergence and convergence. And so that's how we get on this side, or the east side of a trough, we get divergence. On the west side of a trough, we get convergence. Or if you're looking at it around a ridge, on the west side of a ridge, we get divergence. On the east side, we get convergence. So that's what I have written out here. And this is all, again, due to convergence and divergence, where we tend to get this pattern showing up, where, again, we have convergence, creates downward motion, which results in high pressure at the surface, and we develop these systems here. Or we get divergence aloft, which tends to create upward motion, which is associated with low pressure systems at the surface. The exact details of how these all connect together, and also connecting them to fronts and air masses, that will be in the synoptic features lecture coming up after this one. So that gives our sense of synoptic scale. Next up, moving on down to smaller phenomena, is mesoscale. This is where we have sizes typically in the 2 to 1,000, a pretty substantial range, kilometers. And because of that substantial range, there's a lot of different phenomena that fall into this general category. And this includes a lot of things that we care about in this class, like thunderstorms and thunderstorm complexes. Tropical cyclones are on the upper end of this. Precipitation bands within various systems fall into mesoscale categories, as well as smaller boundaries of air. Fronts are typically, the broad scale fronts are in the synoptic category, but our little fronts, things like gust fronts, outflow boundaries, talk about those just here are a couple slides, and also sea breezes fall into this mesoscale category. So one of the key mesoscale phenomena that we care about are thunderstorms. And really what thunderstorms are is that they're rapidly rising columns of moist air that condenses to form liquid and ice that make up a cloud. And because they're rapidly rising so much and they have all of that energy, they end up going up. The thunder part comes from lightning and the charges created by this rapid movement of this ice and rain. But then we also get precipitation because there's so much of it that condenses or deposes out into either liquid or solid precipitation. It has to go somewhere and it falls down. And the ingredients that go into thunderstorms are warm, moist air in low levels to sort of have that source for this rapidly rising column of moist air. We have to have steep lapse rates so that there's enough buoyancy for this to actually happen so that this air can move up, because if lapse rates or the rate of change of temperature aren't steep enough, they're too slim, it doesn't change enough, there isn't enough buoyancy so that these parcels of warm moist air can't go up. Again, I'm doing this gesture a lot, but that's what upward motion in the atmosphere looks like. And because with our last little ingredient, because otherwise things will just stay steady, we have to have something to kick it off, whether it's a front or some other kind of boundary causing movement this way that displaces something upward, or like a little warm bubble or something caused by a particularly warm or light absorbent piece of land. All different things that talk about can trigger lift to get a thunderstorm starting up. And in a very high level overall sense, thunderstorms act to neutralize the imbalance that these steep lapse rates or large rates of change of temperature with height have. Or warm bubbles at the surface, where we have these warmer, moist pockets of air lower down, it acts to try balancing these things out because, again, the key idea to atmospheric motions is that it's trying to bring this unequal distribution of energy into and towards a closer equilibrium state. Of course, again, because it's constantly fed with more energy from the sun and more is radiated out through long wave, it never reaches a perfect balance. But the tendency in the physics tends towards this correction, and that's why we get things like thunderstorms or really any other kind of weather that we have. And the net effect is that it transports this energy upward from the surface, where we get a lot more of that because of absorption from the sun's radiation, upward in the troposphere. So that was talking about thunderstorms on the way up. They also, a lot of things happen on the way down. Mentioned thunderstorms form precipitation, and that doesn't stay in the cloud. It falls out because it's precipitation. That's basically its definition. Some of this, though, evaporates. And we talked about before, evaporation tends to cool air. And because cooling air tends to increase its density, decrease temperature, increase density, tends to sink. So the air gets cooled because of evaporation, and it tends to fall with the precipitation. And so we get this cool, moist air coming out of these clouds, and which it sort of spills out like you would imagine just spilling water on on the ground or anything like that. That it spills out and then spreads out. And this we refer to as the thunderstorm's outflow. And you can see a nice little animation of what this looks like on radar. We have these storms popping up, and then the cool, moist air that spills out from beneath them ends up forming this sort of bubble, or this where it's all spilled. And the boundary, which is what shows up most clearly on this radar imagery, is what we call an outflow boundary or a gust front. And that will become important later on as well. The other thing to talk about is that on a mesoscale level, again, up to 1,000 kilometers in scale, these individual thunderstorms and their outflow boundaries can interact to create larger complexes or larger organized structures of thunderstorms. And so we call that the mesoscale organization of thunderstorms. And there's a lot of these patterns that occur often enough that we recognize and work with them and give them certain categories. This first one up here, we call these are cells. They're individual thunderstorms that are formed cells, and they tend to be organized in this cellular way where we can see them all distinctly. We also have patterns that are we call lines. They're linear systems where there's enough thunderstorms that they all look sort of jumbled together into a single cohesive pattern that looks like some kind of straight line or little curvy line. And the other precipitation that comes out from the main convective core, where our main updraft is, and then spreads out into what we call stratiform region. We also have bows or bow echoes, which is sort of a subcategory of these linear systems where there's so much curvature due to strong flows that reinforce, and we'll go into all this more detail in the severe thunderstorm section. But we get these bowing patterns, and those are especially indicative of strong winds. And then we can also get various scattered forms of, or less well-structured forms of thunderstorm organization. This is what my current research project is all on. I'm trying to apply machine learning to this problem. So if you're interested in this at all, feel free to ask me anything about it, because I definitely, this is what I'm most interested in probably when it comes to meteorology at this point. So that wraps up our sort of mesoscale overview. Then we go on to microscale, our last category. And we won't talk about this a whole lot, just know that it's there. This refers to really anything that's below that 2 kilometer size threshold. Phenomena that fall into this category include tornadoes. We will talk about tornadoes in this class, but mostly as they're associated with thunderstorms. So they still sort of fall into that mesoscale umbrella because tornadoes themselves only occur with thunderstorms. Otherwise, there's some form of landspout or something like that. Also in this category include things like dust devils, and I said landspouts, and various other rotational things that spin up on this scale. And turbulent eddies. Again, another thing that spins. This is less about coherent structures that spin in this direction. And turbulent eddies are just really anything that spiral around. If you've ever blown out a candle and seen the smoke billowing up, that forms turbulent eddies. And that falls under microscale as well, which is a very important area of meteorological study, and one of my other research projects focuses on that as well, but won't be a focus area of this class because we focus mostly when we're talking about these severe and hazardous weather phenomena on the synoptic scale and mesoscale. But at the end here, just want to provide, again, a summary and try bringing this all together. We have generally 4 scales of weather in meteorology that are separated. We usually set the categories by their distances, and they're all listed here about sort of the characteristic lengths that these phenomena in each of the categories occupy in the atmosphere. So we start at the largest, at planetary scale, where we talk about things like jet streams and the general circulation and large-scale wave patterns. Then we go to synoptic scale, where we talk about individual troughs and ridges, and air masses, fronts, and large scale weather systems like high and low pressure systems. Then we go to mesoscale, where we have things like thunderstorms, outflow boundaries, and thunderstorm convective or tropical systems. And finally to microscales, where we have things like tornadoes and small isolated clouds and turbulence. And so this is the general picture of the scales of weather. So that brings this lecture to a close. The discussion post for this week is up. It's broken up into two parts. The first, where you're just trying to find maps, some at each of these scales, not microscale, because we typically don't have good real-time observations of all of that. But finding for a severe weather event, a planetary scale, a synoptic scale, and a mesoscale figure, and then the reply, which is later after we can have the lecture videos up about those various synoptic scale details. The reply will then actually ask you to describe what's in each of those categories and those maps. Also, those lecture videos are coming up in about the next day, along with the quiz for this week. And just a final reminder at this point, we're in week 3. Week 4 is sort of an important week in this course. That's when we'll start focusing instead on this broader overview that we've started off the course with. We'll be actually getting into talking about specific severe and hazardous weather phenomena. It's also, I've had a couple questions about the final project. This is when I'll be putting together and sharing with all of you the rubric and the details about that final project. So be sure to pay attention next week for week 4 for those details. And I will see you next time when we talk about air masses, fronts, and large-scale systems. Thank you.